So thank you so much for the invitation. And I've been using this picture, and yesterday I did some playing with models that generate images from this image of the School of Athens, and try to do it by yourself on some of these generative models, how you generate the School of Athens, and you see some of the very interesting issues that we have been discussing. But the idea here is that this is a symbolic representation of knowledge and the importance of knowledge in the past, or at least in the Western world. So I use this as a symbol, the importance of knowledge, and also as a symbol, as a pictorial representation of something. So a symbol is not only a variable in logic, but or a term or whatever we define as a symbol, but also a physical representations, or the way you interpret them can be grounded as symbols. This is a little bit of the talks of the points I will talk over here. The evolution of AI and how its impact is indeed connected to reasoning and learning from day one in AI. Revisiting some of the challenges for Neurosymbolic AI, not that we need to revisit many of them, because we've been discussing this for over a day here and for many, many months on other media. And also a few conclusions moving forward with the field of Neurosymbolic AI. So if you want to have a general idea of our thoughts, you can consult this paper that Arthur and I published recently. We kind of gathered a lot of evidence and a lot of approaches that we deemed were relevant to the general audience in Neurosymbolic AI. And also we present a number of open points that are relevant for further research in the field. So I'm someone who is very, very interested in history and the evolution of science and knowledge. And we are, especially when we perceive that we are living through a phase transition. One of the important points in history was when people realized that spreading knowledge would give a lot of power to people. And today and yesterday we saw some claims or some statements saying that, well, knowledge is not that important. You can build things from scratch, but any evidence in history contradicts the assumption that we don't need knowledge, or we can start from a tabula rasa. And this aphorism from Francis Bacon is one that I like a lot. Everyone, of course, knows it, but the point here is to emphasize the role of knowledge here. That is very important in Neurosymbolic AI. Another point that I like to make is that when we go through these transitions, there's a lot of noise, a lot of misinformation, and a lot of misinterpretations about what's actually is going on. In the beginning of the web, we thought that the web would be very useful to access documents in a linked environment where I could access my papers and my writings very effectively, and then science would be made more efficient at CERN for physicists and for people who are distributing their knowledge across their local communities. But the consequences were unimaginable, as we can see over here. The same thing happens in AI, but we as researchers in AI, we tend to be sometimes overcritical. One of the key points that happened in the last 30 or 40 years, maybe, at least to my perception, was when IBM Deep Blue finally defeated Garry Kasparov. I think that was a great achievement for technology, for engineering. And also, it showed that some of the challenges that were put forward in the 50s, like defeating a world chess champion, was something that became feasible. And this is a great achievement. And even Garry Kasparov has said that he was the first knowledge worker displaced by AI. So I want to emphasize knowledge again, right? He has said that publicly several times. And in the end of the day, you want to see what's the point here in discussing this history and talking about Neurosymbolic AI. And just before the launch of this very popular large language model, ChatGPT, there was a piece on the communication of the ACM, who is the flagship publication of the key scientific association in computer science, about Neurosymbolic AI, and about the need to develop systems in machine learning or in deep learning or in AI in general that are more rigorous, that they follow the tradition, the very beautiful tradition of computer science that stem out of the pioneering work of many people in the 50s and 60s, were academic rigor and even the capability of interpreting any computational object or any computational constructions as a mathematical object. That's a point of view defined and defended by many, including mostly Dijkstra. If one still reads what Dijkstra used to write, and this is all deposited in his webpage at the University of Texas, Austin, you see that computing for the people who defined the field in the 50s and 60s was an extremely rigorous endeavor. And we see that the same should be followed in the machine learning community. And again, I bring things here, Alex, that are not considered today state of the art. When you read something from 2017 these days, you think, wow, this is too old. But the challenges are still over here. And this report was written by the leading figures in AI, at least in the UK, and some invited people from abroad, about the challenges that machine learning was facing in 2017. That was the time when we said, well, you know, machine learning is going to replace everyone that works in any task, and will replace doctors, will replace the drivers, and will replace most of human activity. And we see that those challenges pointed out, it's like 6 or 7 years ago, they're still very relevant to us, and they were discussed at length, including in the panels at the AAAI main conference. And some of these challenges are very, very relevant to this community, including interpretability, including verification and validation, as we said yesterday in our panel, and including the point of security here. And security is very important these days, as we see that computing technologies and AI in general become more and more relevant, not only from an individual point of view, but also we cannot deny that the world now sees AI as a strategic technology for the development of countries. So this is becoming more and more relevant. And we all know, those who have worked in developing large-scale systems, that vulnerabilities are something that are threats that any systems can face and have to respond to. So, and what about language models? What about the current state of AI and the connections with Neuro-Symbolic AI, or what I say, what about with connections with the principal approaches to build integrated learning and reasoning? Even the people who created foundation models, this is a report or something based on a study of Stanford University, they say that there are shaky foundations of foundation models, of large language models, or the misspread or the misrepresentation of information that people are, benefiting from the use of such technologies. And we believe that when companies start using more and more these technologies at length, or people start using these technologies in an uninformed way, we as researchers have to make sure that what we're offering to society are technologies that are safe and secure, because the users, or millions of users of those technologies, they don't have enough knowledge to understand the risks that they are facing, right? So issues like verification, validation are extremely important, and so are the ethical consequences of the use of those technologies. And many in this community, and including Gary, who was here speaking to yesterday, they have seen that and have pointed out, not only us, but many people who are working on AI now, that there are benefits in using logic-based or symbolic techniques. And the key benefits that I see here is that symbolic systems, and it's even said here by Gary, is that symbolic systems are verifiable systems, or are systems that you can check those models. There are some techniques that are extremely successful in, let's say, mainstream computer science, separating from AI, and those include software verification and model checking. Model checking, for instance, has a huge history of success, especially in the hardware industry. Those who are experienced enough, like myself or some other people in the room, might remember the early case of the Pentium 5, was it Pentium 5, Ben? That had some problems at the Pentium 5 chip by Intel that had some problems in the calculations that it performed. And that was a kind of wake-up call in the chip industry, that they realized that using techniques like model checking and formal verification was extremely important for the success of the industry. And we might realize that in AI, by combining those techniques with machine learning, combining symbolic techniques, combining reasoning techniques of learning and reasoning in a rigorous way, in a way that, for instance, people like Les Valiant, who is a Turing Award winner, has defended for the last 20, 30 years, is the way forward to developing richer cognitive models. So the key questions that we tried to answer, at least from our perspective, was how machines think and how this thinking process can also help us to understand how we think. This is a question that was posed by Turing in his first or his most famous AI paper published in the journal Mind. And also in some of his talks and some of his interviews that he gave at the time to the BBC. So Turing was actually quite a popular person already in the 40s and 50s. He was well known, at least to the well-informed public. And one of the key questions here is that we want to define, we want to understand, and he wanted to understand the thinking processes by understanding how artificial thinking machines would perhaps think. Right, and but the other point that we want to also to make here is that those people who are pioneers in the field, they were interested in understanding the connections between the different approaches that were being used at the time. Even von Neumann in the 1950s, and if you read some of his papers in a volume that was edited amongst others by Shannon on automata theory, he already realized that between logic and automata, there was a connection through intuitionistic logic, which is a non-classical logic that explains how you build constructive proofs. And why this is important? Because in computer science, anything has to be constructive by definition. We only work with algorithms. Even in AI, we only work with algorithms. And von Neumann realized that there was a connection between the first artificial neural network models and intuitionistic logic. So we can say that these connections between the two fields, between learning and reasoning, between logic and neural networks, or between the connectionist school and the symbolic schools is something that goes back and has a long history in AI. Even the first paper that was published in artificial neural networks, let's call it the first artificial neural networks paper by McCulloch and Pitts, even in the title of the paper, you had two apparently contradictory things happening at the same time, like a logical calculus of ideas immanent in nervous activity. So the first examples that you have in the paper are how to process binary operations or binary logical operators. So Neurosymbolic AI, one can claim that has this long history in AI that goes back at least to the 40s or 50s or 60s, because even Turing or even McCulloch and Pitts, or even von Neumann, were people who saw these connections and saw that there was some ground that could be made in building forward two schools together to understand richer models of computing, richer models of AI. So, okay, moving now to our times, one point that I sometimes make clear is that Fabio Cosman was mentioning yesterday that one of the proxies to have your paper rejected in the early 2000s for the New RIPS conference was if your paper had neural networks in the title or in the abstract, right? So neural networks have not always been very popular, but from 2006, mainly, in 2006, Jeff Hinton published this paper that it was, at least for some of us, the first time that deep learning or deep networks were explicitly mentioned in the modern sense. In the modern sense, I mean the sense that we see or the interpretation that we give to deep neural networks or deep learning from 2010, 2012, after the success of computer vision and image recognition. And the curiosity here is just, very cheap publicity, is that in the same issue of neurocomputation, we published a model for neurosymbolic reasoning and learning about epistemic and temporal reasoning. So, of course, Jeff Hinton got his paper with thousands of citations, and this paper here is not very well known, but we put forward some of the principles of neurosymbolic AI in this paper. And the point I want to make here as well is that for some reason, after the great attention that neural networks and deep learning got from 2010 to 2018, 19, people realized, oh, there is one problem here. Sometimes we realize that we don't know what's actually going on, so how we interpret these things. And so by 2020, people started going back and they realized, well, you know, there is this theory of system 1, system 2 by Kahneman, and also there's this small community of people that work on representing symbols within neural networks. And what they try to do is to show what kind of computation neural networks are doing from a logical perspective, from a logical point of view. And then we had like a large number of people getting more interested into Neuro-Symbolic AI. Also, Fabio mentioned yesterday Henry Cox's talk on the 3rd AI Summer on how to classify Neuro-Symbolic AI systems. There was a fireside conversation at AAAI 2020, just before the pandemic in New York. And in this conversation, this panel was very interesting because Daniel Kahneman, who is frequently cited in AI, he said that for him, there is a symbolic representation of cognitive processes in the brain. So I think that that was a turning point for the field of neurosymbolic AI, when people like Daniel Kahneman says, wow, or states that symbols are very important to cognition, very important to reasoning, to thinking, to learning, especially when one works on that analogy, system 1, system 2, that Kahneman and Tversky have defined for 30 years. Also, some of the parallels between system 1, system 2, and neurosymbolic reasoning can be drawn in several domains. In our book, that's mostly a book based on foundations. And what we study in the book is not exactly how neurosymbolic AI will be a technique that will be, according to Gartner, and as mentioned by Alex yesterday, it's something that is on the innovation trigger here that might happen in 10 years. In this book, what we try to do and what we show is how certain fragments of logic, and many of them, Benjamin, represented via prologue fragments or inspired into logic programming, can be computed in artificial neural networks. And Alex was also asking, okay, what is industry making about neurosymbolic AI? If you go back and you consult the main labs of industry or companies like IBM or Microsoft, or more recently DeepMind and Google, you see that neurosymbolic AI is kind of getting off some attention. And I especially like this paper recently, and I just read this paper that got some attention on Twitter, this paper from DeepMind Google. And what I think it's very important to realize here is that deduction, induction, or symbolic deduction, or systems that work on constructing proofs using artificial neural networks, they can be shown to be extremely effective. And to me, this is one of the best examples of neurosymbolic AI working in a technological application. We started by representing certain fragments or certain subsets of logics within artificial neural networks, and I will show some technical details about how we did that over in our research. But what I think here is that starting from logical or mathematical problems or reasoning tasks might be the way forward for neurosymbolic AI. And this is one example of a system that works very well. Another example and another evidence that I want to show is a recent book, a recent short book written by none less than Stephen Wolfram, saying that thanks to the success of large language models, he sees that now there is finally, and I quote him, the opportunity to combine those two approaches in AI to make stronger AI systems. So there are other people thinking that, well, you know, AI cannot only be developed by using the typical approach that is using in machine learning. And I have to say that I like that approach. I'm not a person who sees an opposition in those two schools. I've been using neural networks in my work for more time than I wish I have been using. It just means that I'm kind of getting old, over 25 years. But I also come from a school that sees a lot of merit on rigorous mathematical foundations and proofs and verification and building verifiable systems. So the examples that we are seeing here is that people are realizing that exactly the understanding how natural language specifications that are used as input to language models, or how we can search for better explanations to the black boxes that we have that have become very popular today in the AI community. And the key question that I want to make here, and not to miss the point, is that these debates can perhaps lead to better integration and to better science. I don't see an opposition between the two schools. And again, to quote someone who has been very influential in AI, even though he's not an AI researcher, Daniel Kahneman. Daniel Kahneman said that as far as he's concerned, System 1 is the fast system, certainly knows language, and System 2 does involve certain manipulation of symbols. And he said that at AAAI 2020. So considering that those intuitions and those statements come from people who have been studying cognitive reasoning and reasoning or human reasoning for a long time, and we want to mimic the kind of work that is done in cognitive science or is done in neuroscience, we believe that there is a way forward here for AI in combining those approaches. Okay. From our perspective, how we build neurosymbolic AI systems that are well-founded. We all know that there is a need for systems that learn from changes in the environment. It has been said here for many times. Perception is something extremely important. It was said many times in the conference, how to build systems that have better perception from the environment. And reasoning about common sense knowledge that includes reasoning about space, reasoning about time, reasoning about uncertainty are also challenges that the AI community has faced for many, many years. Tony Cohn was here yesterday, and I was a big fan of his work during my PhD studies. He developed several calculus and logics for reasoning about time and space. And this work can be extremely important here in neurosymbolic AI or in machine learning, because as we build richer models, we have to have better abstractions, better representations for the dimensions, or for what they call today the modalities of reasoning or the modalities of AI. And there is a logic called modal logic that deals exactly with modalities of truth. So why not thinking about modal logic? And another point that I want to make here, this is a picture of my daughter when she was very young. I am not a cognitive psychologist. But what I realized was that with very few examples, apparently, she was capable of learning how to do some tests that we used to perform on her, like brushing her teeth. And then the first time that we are trying to teach her how to brush her teeth, she took one of her first dolls and said, wow, this is what, how you should brush your teeth as well. So they combine abduction, induction, and explanations, and in order to perform the tasks that they are learning. And learning is an extremely hard activity, and formalizing learning is even harder. I can tell you that, just to open a parenthesis here, I'm learning to ice skate from a very later age. I didn't grow up in a cold place, and I can sympathize with children when they're learning to walk. Right? Try to learn to walk on ice after you are 40. Then you are understanding how difficult it is to learn to walk for a child. Right? Okay. So how we combine learning and reasoning in our approach. So our approach used the pioneering approach, or one of the approaches that I like to mention about, just to make a point that neural networks can indeed perform logical inference, at least sound logical inference over fragments of certain logics that can be represented nicely as logic programming or adaptations of logic programming, right? The key idea here, and I present the idea of connectionist model logic, is that we see the artificial neural networks as model logicians see possible worlds. So if we could build connections between multiple ensembles of artificial neural networks, we could draw a mapping between those ideas of having multiple ensembles of artificial neural networks and the idea of possible worlds, Kripken possible world semantics. Also, this idea also fits very nicely for idea that people use state machines or state models for temporal logic in software verification. Then you can have an adaptation of this idea or a mapping of this idea to model checking in the future your neural networks, if you have a way of specifying your neural networks in a rigorous way. So that was the key idea that we had at the time, how to represent those relations between possible worlds within a neural network system or within a connectionist system. And the key idea was very intuitive, the intuition you have in mind. So what we want to say here is, okay, we can represent certain fragments of logic, certain fragments of model logics, and we pick model logics because they are very good to represent interactions between multiple agents. There was a talk by Leslie Kaubling from MIT about robot execution and neurosymbolic robots and reasoning about robots. And the questions I have about that brilliant work that she does for over 30 years in robotics is how you build systems of robots that interact with each other, right? So perhaps there is a theory underlying many of the principles of the problems, for instance, temporal synchronization, temporal learning. Just think about, for instance, the dining philosopher's problem. Imagine if you put some robots across a table and you teach them how to synchronize the use of resources that's in the Dijkstra's dining philosopher's idea. So that would be a very nice piece of work to show how Neurosymbolic AI can implement safe semantics. So what we did here was we showed that it was possible to build algorithms that would compute the inference rules or the decision procedure rules of model logics within a connectionist framework. And we call the systems connectionist model logic because we saw the connections or the relationships between possible world semantics and neural networks, right? So there are some algorithms that we designed to build those connections. And what we showed in these papers is that the fragments or the model fragments of logic programming, they were executable, and I quote, executable within a connectionist framework. It means that the fixed point semantics of those restricted programs could be computed using an artificial neural network model. And we showed that for several fragments of logic, including temporal logic, linear temporal logic, logics of knowledge, and so on. So this kind of open several possibilities, and this is one of the algorithms that is on the paper. Here is a pictorial representation of solving the Madhyastha puzzle or solving, for instance, the Monty Hall puzzle. We extended this work to represent a solution for the Monty Hall puzzle and several other puzzles. And the thing here is that we can show that neural networks can approximate the meaning of these programs, can approximate the semantics of what those programs do. And of course, the biggest challenge was how we represent temporal evolution in time, how we represent knowledge that evolves in time. So there is a complexity issue here that's important because as you grow in time and as you increment, as you add more and more knowledge, of course, your neurons, your network, or your knowledge that is represented is going to grow in time. But it seems to us now that you have all this memory, including large language models, that the explosion or the state explosion problem is not seen as relevant in today's AI as it actually is from a theoretical point of view, right? So this was the kind of work that we did in the past. This was one of the key intuitions, and we did this. We did an approach to represent and learn several fragments of different logics. And one of the key aspects that one of the key applications that was very neatly represented in artificial neural networks was an approach that Fábio Cosman and his group is following in Brazil. If you are trying to do a value-based argumentation framework, this theory of argumentation framework also fits very well into the framework of connectionist models. So I'm pretty sure that his work is going to have a lot of attention in the near future because he's dealing with a much larger set of arguments stemming from language models and stemming from a much larger set of information and arguments, of course. I will finish. Okay. And finally, another work that I also consider to be a promising approach to neurosymbolic AI is the approach based on graph neural networks. Graph neural networks are very rich representations. They were created in the early 2000s by a group led by Marco Gori, who has also been in this community, Marco Gori and Franco Scarcelli in Italy. And those papers have become now very highly cited. And another point that we use some argument here that someone who has a lot of experience is Sepp Hochreiter. Of course, you know him because he created a long short-term memory model with Schmidt-Huber. He says that perhaps the most promising approach to build broad AI, and broad AI means of course, we all know what's broad AI in this room. I don't need to repeat what's broad AI. One of the key points here is that he makes is that graph neural networks are rich enough to represent a lot of knowledge and several different problems when you have to deal with abstract structures as graphs do. So this is another point that I want to make sure that we make in this talk. Finally, I want to mention here, Asim, I'm going to finish soon. 1 minute, 2 minutes, 10 minutes.
1
minute, okay. According to Les Valiant, in his book, probably approximately correct, Les Valiant is someone who created the foundations of modern machine learning, the pack learning model, learnability model, and it's also someone who sees the need for integrating learning and reasoning in a principled way, in a tractable way, and using methods that are extremely rigorous. If you know Les Valiant, all his works have a very sound theoretical foundation. As Benjamin was mentioning yesterday, the very small community of machine learning in the 80s that was about the size of this room, they were very, very rigorous people, including Les Valiant, right? And from our point of view, from the point of view that I do research on Neurosymbolic AI, that is trying to understand what kind of logical inference connectionist models do. That's the specific topic within Neurosymbolic AI that I am more interested. What kind of logic you have within neural networks, right? We are still in search for several answers. One of the answers is, okay, how to perform proper first order logic or proper higher order reasoning, because this provides you richer information about relationships between objects, but of course, in a principal way. We know that first order logic's undecided, but of course, we are dealing with fragments here. The second point is how to deal effectively with common sense reasoning. Common sense reasoning remains a challenge in AI, right? And perhaps the way to put forward is to understand how connectionist models or how graph neural networks or other model that you develop can learn to solve problems that are hard. For instance, there are some people scratching the surface of solving combinatorial problems using neurosymbolic approaches. We did some work along these lines as well that we thought was promising. And finally, that a point that connects very well with the current state of AI is how to build effective and principled human network communications, where we see the interaction between people and language models and people and generative AI tools as a part of a multi-agent systems that is interacting and generating answers that are understandable, that are explainable, and we hope that are sound, and we hope that are useful and do not offer any risks for people. So the theory of multi-agent systems in AI was developed considering artificial agents, but now that we have this interaction between real agents and artificial agents, this human network communication theory can perhaps be better explained by taking the formalization that we developed in multi-agent logics, combined with the formalizations, hopefully the formalization that we have for large language models. And this is mostly what I had to say. I had some pointers for the recent literature, including the work done by Alex, the work done by many people in this room over here. And I leave you with a few quotes from the past, but I think that they are very relevant to the current research in AI, including by Joe McCarthy, where he also is someone who sees the relevance of common sense knowledge and reasoning. So we need to always have in mind that the bigger picture of science with respect to our own local interpretation of the restricted community that we are living on. Thank you. Thank you so much.
Thank you. So we have time for one very, very quick question, and later we'll have time for discussion with Louis. So if you have more questions.
Thank you very much for the great help. I have a question about the common sense. I mean, to my understanding, working on natural language processing, it seems that common sense has been really not approachable with the classical AI, and it seems that formalization of common sense is more challenging than like other areas. But and I think probably what language models did is really like a breakthrough in like common sense reasoning somehow.
Agreed.
in their own way. So do you think we really need to go for formalization of common sense as well in the neurosymbolic, or that is something that we can stay with this sloppy understanding of the world and context-dependent understanding of the sensory data?
I think we should move forward. I mean, we should keep doing research on common sense reasoning, because all the examples or many of the counter examples that we see in today's AI are connected to common sense, even in the vision world, right? When we see things dropping from, ice droplets from glasses of water and people disappearing. So common sense reasoning seems to be understood from a language perspective, but the representation of them, the internal representations in those systems, we still don't know exactly what are the best ways to do it. And I do believe that common sense reasoning and common sense learning remains a big challenge. Some people say, well, language models solve language, but to what extent? Not to certain points or to certain, in certain challenges, especially when you combine spatial reasoning with physical properties in the counterexamples or in the examples that we have seen now just launched by certain companies, right? When you look at those very nice representations of reality, we see that there are some common sense failures or common sense errors, to be honest, that a child would realize that it's wrong. So I don't think that the formalization of common sense reasoning is a solved problem.
Thank you.